Everyone, so today we're going to start off our study of chemistry by looking at the fundamental laws of the discipline. These are the laws that I think often we forget about as we go through our study of chemistry. We learn how to balance equations, we learn how to do stoichiometry, but there's some laws that underlie all that. There's a reason why we can do all that. And so that's what we're going to talk about in this presentation. So the first law that we're going to deal with is the law of conservation of mass. This guy over here, Antoine Lavoisier, came up with this, and he was a French scientist and was meticulous with his measurements. And what he did is he performed a lot of chemical reactions, and he measured the total amount of products before, and the total mass of the reactants rather before the reaction, and then the total amount of products after the reaction. Compare those two masses to very, very precisely. So from this, he came up with this law that in any physical or chemical process, that the mass is conserved. Mass can't disappear on you. It can't pop out of nowhere. And we use that every time we balance an equation. So shown here is one of my favorite equations. This is the thermite reaction. So you react solid aluminum with iron oxide. And in doing that, you make a lot of heat, so you actually create liquid iron. It's very, very cool. And you also make solid aluminum oxide. But notice when looking at this equation that the number of atoms are not equal on each side. So we have one aluminum atom, as shown right here, and we have two on this side. Same thing happens with iron. So when we balance an equation, and we put 2 in for the aluminum, we put 2 in for the iron, what we're doing is we're making this obey the law of conservation of mass. We can't have iron atoms just disappearing, going from 2 to just only 1. And we can't have aluminum atoms appearing out of nowhere. So as applied to chemical equations, the law of conservation of mass says that we need to have the same number and type of each atom on each side of this equation. Okay, simple enough. The next law is the law of definite proportions. This was devised by the work of Joseph Proust. And what this says is that if you take two samples of a compound, with made up of the same two elements, that the mass ratio of the elements in each of these samples will be the same. So it doesn't matter where you get these samples from, whether they're man-made or artificial. If it's the same compound, it'll have the same mass ratio of all elements in that compound. And so what I have here is some data, two different compounds. It's the same compound, just different masses. One's 20 grams, one's 30 grams. And if we look at the mass ratio of this, so for compound 1, we look at the ratio of, grams of fluorine to grams of carbon. And what we would see is we would take 18.44 grams of fluorine divided by 1.56 grams of carbon, and we would have a mass ratio of 11.8. So that's the mass ratio of fluorine to carbon in compound 1. Compound 2, which again, it's the same compound, just maybe a different sample or a different mass. We do that, again, take the grams of fluorine to the grams of carbon. We get 27.66 grams of fluorine to 2.34 grams of carbon. And again, we get 11.8. So this mass ratio of fluorine to carbon is the same in both samples of the compound. And that's what the law of definite proportion says. Kind of wrote over that a little bit. But two samples of the same compound will always have the same ratio of elements by mass. The final law that we're going to talk about today is the law on multiple proportions. And this was devised by John Dalton based off the work of Joseph Proust. And what this says is that if you have two elements and they can make two different compounds, if you take the ratio of the masses of the elements in each compound, the ratio of those masses will themselves be a whole number ratio. Okay, I know it sounds a little confusing. Let me show you, and I think it will make a little bit more sense. So we have two different compounds of carbon and oxygen, compound 1, compound 2. And these are not the same compound anymore. So this is the difference between the law of multiple proportions and the law of definite proportions, is that the law of definite proportions, we're dealing with two samples of the same compound, Whereas with the law of multiple proportions, we deal with samples of different compounds but the same, two elements in them. So for compound 1, what we're going to do is again take a mass ratio, and this time we'll take the mass ratio of, sorry, I just realized this says chlorine, it should be oxygen. Sorry, guys. So we're going to take the mass ratio of carbon to oxygen, so grams of carbon divided by grams of oxygen. And that will be, this is offending me, this will be 6.43 grams divided by 8.57 grams, and so this will be 0.750. For compound 2, we'll again take the grams of carbon to the grams of oxygen, but remember these are different compounds, so we're not going to get the same ratio. We'll get 2.73 grams of carbon divided by 7.27 grams of oxygen. So this gives us 0.376. Okay, so these again are the ratio of the masses of the two elements for two different compounds. Now the next step, the final step in the law of multiple proportions, is we now take the ratio of these two numbers, so this number and this number. And so for compound 1, 0.75, for compound 2, 0.376. And that will equal 1.99. So there's about 2-to-1 ratio. What that 2-to-1 ratio says is that there's twice as much mass of carbon, so by mass, there's twice as much carbon as oxygen in the first compound compared to the second compound. So if the first compound has a formula of CO, if there's twice as much carbon in this compound compared to compound 2, this has got to be CO2. Okay, so if we double the mass of oxygen by adding another atom, then essentially that ratio of oxygen to carbon gets cut in half. Okay, and that's what the law of multiple proportions says, is that if more than one compound exists composed of the same two elements, the ratios of the masses of the elements in the compounds will themselves be a whole number ratio. So when you do this, that's what you're looking for. It's not that these two are going to be a whole number ratio. The masses of the elements in each compound won't be a whole number, obviously. But if you take the ratio of those masses, the ratio of those ratios, you should get a small whole number ratio. Okay. Now, the challenge for scientists was to explain why these laws were true. These were determined experimentally. From my descriptions, by calling this one CO and CO2, there's this idea that there's atoms, but when they did these experiments, they didn't know about atoms at the time. It took John Dalton to devise the atomic theory. And this atomic theory explains, those three laws, why they exist. If everything is made up of atoms, then these atoms can't disappear or reappear, and that explains the concentration of mass. Because we have discrete particles combining, it also accounts for the law of definite proportions and the law of multiple proportions. So this is the atomic theory, one of the most important theories in science. It underlies everything that we do in chemistry. And again, it arose from the observations of the law of conservation of mass, the law of definite proportions, and the law of multiple proportions.